Hello, Chem 112. It's Virginia here to go over the acid basics, talk about what makes something an acid or a base, what kind of reactions will they undergo, and then what will the pH of the solutions end up being after those reactions. So here I've drawn a volcano, which is a nod to that classic elementary middle school science fair experiment where you have the baking soda and vinegar volcano. And so there's my email in case you need to contact me. But otherwise, let's go ahead and get into it. And the worksheet we're going to go over is posted on the ebook in the handouts and materials page. Okay, so let's look at the three different definitions for acids and bases. The first of which is the Arrhenius definition. So Arrhenius said that acids drop off protons in solution, also known as H+, or hydrogen ions. And Bronsted-Lowry said the same thing. Easy enough to remember. And those are the definitions we usually are working off of. Our other definition are our Lewis acids, and these accept electrons. So these are usually small positively charged species, like metal cations, or compounds that have boron as the central atom. Usually what we see most frequently is BH3 or BF3. Okay, so let's look at what those people said about bases. It's a little more complicated here. Arrhenius said that bases drop off hydroxide in solution. So this would be like our sodium hydroxide, calcium hydroxide, etc. But then Bronsted-Lowry came and said, it's not so much that they donate hydroxide, it's more that they accept the H+ given off by acids. And so this is the definition we most widely accept. And then we have our Lewis bases, and these donate electrons. And these can be anything with a lone pair. Okay, so those are our definitions. Let's go ahead and look at how those actually show up. And so they want us to list the 7 strong acids, and I can't stress enough that it's worth just memorizing these. Make flashcards, make a PowerPoint presentation, write them down over and over again, tell all your friends, whatever it takes to memorize these. But those 7 are HCl, HI, HBr, HNO3, H2SO4, HClO3, and HClO4. Okay. And then we have our 8 strong bases. And these are easier to remember because they end up making a sort of B on the periodic table when you look at it. And these 8 strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, rubidium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. And so you can see sort of the B that they make on the periodic table, because these are written in order. And you'll want to be careful with the stoichiometry on some of these, because for calcium, strontium, and barium hydroxide, they'll dissociate to give you 2 moles of hydroxide for every 1 mole of your initial salt. Okay, so then they go on to say that amines are classic examples of weak bases. So amines, if you remember your functional groups from Chem 110 or other classes, they are oftentimes written like this. And it's a nitrogen with three bonds and one lone pair. And our favorite example of this is ammonia, NH3. And when you put this in water, it acts as a base and accepts a proton from the water to make NH4+. And in doing that, it leaves behind hydroxide. Okay. And because this is a weak base, we're at equilibrium, so we have double arrows, and our reactants are dominant. We'll have a really small K, telling us that we only get a small fraction of products out of this reaction, but it does happen, and it will increase the pH of the solution. Next up, we have our carboxylic acids, and the way you recognize these is if you see the COOH on molecules. And one of our go-to is acetic acid, just CH3COOH. And if we put this in water, it will dissociate and it will lose its proton. We'll donate that proton, leaving behind something negatively charged, and form hydronium. And so right now I want to take a moment to make the point that if you see hydronium or H3O+, this is synonymous with just H+, or a proton concentration. You can use them interchangeably. Okay. So now we have our list of strong acids and bases, and we also now are more equipped to look for weak species, whether they're amines or carboxylic acids. So let's go ahead and look at the Lewis structure for some different acids. And here you can see that all of the structures have the same core features, with a chlorine, the hydrogens, which are marked in red, attached to oxygens. And so when we're thinking about acid strength, what we're looking for is which bond is the most polarized and how polarized is that bond. Because the more polarized the bond is, the easier it is to break. And so here we have to think about differences in electronegativity and keep in mind that greater differences in electronegativity are more polar bonds. And so we remember that fluorine is the most electronegative atom. Okay, so if we were to draw in how the electrons are moving, or draw an arrow toward which atom they're more attracted, we can think about which bond is most polarized. So looking at this first molecule, oxygen is the most electronegative atom. So the electrons from the chlorine are going to be drawn toward the oxygen, and even more so is there a difference in electronegativity between the hydrogen and the oxygen. And so electron density is going to move toward the oxygen. Okay. And since this bond is the most polarized, that's the one that's going to break. And the hydrogen will dissociate off in H+. If we look at this next case, now we have this extra oxygen, which is pulling electron density away from the chlorine. We have the same bond dipoles that we did in the last case. And so now we have an even greater overall dipole moment moving away from the hydrogen, which is now making this bond more polarized. And so this would be a slightly stronger acid. And then in the next case, now we have another oxygen pulling electron density away from the chlorine. And so now we kind of have 3 arrows pulling away from the hydrogen. So we have an even greater bond dipole moving away from the hydrogen in this case, making it a stronger acid than the last. And this you might recognize as HClO3, which is a strong acid. And the fact that there are oxygens drawing electron density away from that hydrogen, making that bond so much more polar, is what makes this just completely dissociate when it hits water. And then in this case now, we have an additional oxygen drawing even more electron density away, making this bond even more polarized and making this even stronger. And this is HClO4, which is another one of our strong acids. Okay, so the structure really does affect the strength of our acids, because the more electronegative groups that we'll put near our hydrogen, the more electrons will be pulled away from that hydrogen, and the easier it is for it to leave and dissociate away as H+. So to make any sort of acid stronger, whether it's carboxylic acid or what, we can add more electronegative groups. Now in this question, they want us to rank the acids in order of increasing acid strength. And so here we have a bunch of oxyacids. So we have a hydrogen, a halogen, and then some oxygens. And so when we go ahead and want to rank these by strength, we're first going to look at the central atom. So for these, it's like comparing the iodine to the bromine, because the more electronegative central atom will give us the stronger acid. The relatively stronger acid. They still might be weak, but just stronger than the other ones. And then once we've done that, we're going to look at the number of oxygens. And having more oxygens will give us a stronger acid. Okay, so if we start by looking at the central atom, we have these 3 to consider. And then because we have more oxygens to the right, the HbRO3 is going to be stronger than the HbRO2. And that's going to be stronger than just the HbRO. Okay. And at this point you might have noticed something. We have HI. This is our friendliest of acids, but this is also a strong acid. So of these, this is going to be the strongest, because all the other ones are going to be weak. So being able to just pick out the strong acids is really important, because there might be an exam question where they ask you to pick the most electronegative of the most strong of these acids, and you would just look for the strong acid. Okay. But then this HIO would be the weakest, because it has the less electronegative central atom. It has the lowest number of oxygens. And so what I should really say is for step number 0, look for anything that's just one of the strongs that you've memorized. And then between the weeks, you can go ahead and do those steps. So now we're going to get quantitative